another shortcut rule which can be used to help simplify the process of taking derivatives. Now, the difference in today's rule is that we will be working with something called a composite of functions. Now, we did composite of functions back on the first day or two of the course where we did a little bit of algebra review. And so my first question, I've got two examples up here on the board. We need to be able to take what's called a composite function and split it apart into two separate components. Okay? First thing I want you to notice, what makes this a composite function? Okay? Well, first of all, I have one function, which could be the 3x minus 7, and then I have another function which says take that answer and raise it to the 1/3 power. Okay, so that's what tells me it's a composite. Another word for composite is like a combination. Okay, so we have a combination of two equations put together. And so my question would be is if we saw this combination of functions here, what is the original f of x and what is the original g of x? And the way that we need to break this down is notice that the g of x is the function that's on the inside. It's inside the parentheses here, so it needs to be on the inside of our composite over here. So which is the inside function or the inner function here? Is it the 3x minus 7 or is it to the 1/3? The 3x minus 7. That's what we call our inner function in this particular example, is the 3x minus 7. Okay? Now, once I have the 3x minus 7, what did I do to that function? What was the second part of the composition? Raised it to the 1/3. So what I'm going to do is I'm going to take my answer and raise it to the 1/3 power, x to the 1/3. Now, this is a little different than what we did at the beginning of the semester, because what we started with at the beginning of the semester was we started out with the original functions and we tried to join them together as one. Okay? Just to convince you that this is right, let's go in that direction here. Okay? What if I told you calculate f of g of x, and we didn't have this up here at the top, of course. Okay? What would this be? How would we simplify it? Well, we would be leaving the function f, and what replaces g of x here? 3x minus 7. So now what I'm saying is, if I want to evaluate function f at some number, 3x minus 7, what would I do to that 3x minus 7? It says take your number and raise it to the 1/3. Okay? So my composition would be 3x minus 7 raised to the 1/3, and that, of course, is exactly what we started with up here at the top. Okay? Let's look at the second example, see if we can split these apart. Okay? If we have a function like this, what was the f of x and what was the g of x? Okay, start on the inside. What's the g of x here? That's the inner function, 9 minus 4x. Okay? And then what's the f of x? What are we doing to 9 minus 4x? We're square rooting it. So the f of x on the outside function would be the square root of x. Exactly. Okay? This is something we'll have to get familiar with, and usually we won't write this down. We'll just in our mind recognize 9 minus 4x is the inner function, and then the square root is the outer function. Okay? All right. This becomes very important today because we're going to be taking derivatives of equations that look like this, combinations of functions. Okay? And a good example here that we can begin with, let's say we've got some equation, h of x, which is equal to 3x squared plus 1 quantity squared. All right, this is definitely a composition of functions. We've got the 3x squared plus 1 on the inside, and we've got this squaring function on the outside. Okay? Up to this point, how have we had to take derivatives of something like this? How would we rewrite this so that we could take its derivative? Yes. Up to this point, we had to rewrite this as 3x squared plus 1 times itself, and then we could use the product rule to go ahead and take its derivative. Now, this isn't bad for this example to rewrite it and use the product rule, but what if this number wasn't a 2? What if it was a 7? We really don't want to write this function 7 times and then do multiple product rules with it. That'll take us forever, and we'll probably make a mistake along the way. So the goal today is there a more efficient way to take the derivative of this thing without having to rewrite it as a product? And the answer is yes, and the name that we will give this is called the chain rule. Okay? Now, before we do that though, I do want to calculate this derivative because I want you to see what the answer should be for this problem so that when we start the chain rule, hopefully you can just fill in the missing piece. There'll be one piece that's missing from the answer and hopefully you'll recognize it. Okay? All right, if we were going to take this derivative using the product rule, here's what it would look like. We would take the first component of the product times the derivative of the second component, which happens to be a 6x. Then we would add on the second component times the derivative of the first, which again happens to be a 6x. You know, we basically have two of the same things here. Okay? Now, if we were to simplify this, okay, trying to clean this up a little bit here, don't I have two of the exact same thing? Don't I have two copies of the same thing? Yes. So I'm going to rewrite this as 2 3x squared plus 1 times 6x's. Okay, I have two copies of the same thing, and I'm going to rewrite it in this form and just stop for right now. Okay, there's more algebra that could be done, but I want to leave it in this form. Okay? All right. Now, what if we don't want to actually have to do the product rule each time? What if we want to leave the function in its squared form and try to take the derivative? Okay? Well, let's take a look at it here. Now, what if on the inside here, what if this was just an x? What is the derivative of something squared, or x squared? Okay, we bring the 2 out in front, and we rewrite it as x to the first. Okay, let's try that with this, even though this isn't just an x, let's try that. Okay, what if I bring the 2 out in front, and then just rewrite this as 3x squared plus 1 to the first? Okay, how close is this answer to what it really should be? Very close, isn't it? Okay, the 2 matches up perfectly, the 3x squared plus 1 matches up perfectly. What's the only component that I'm missing? Well, I'm missing the 6x. And my question is, as you look at this original function, where could we get a 6x? From the derivative of the inside, right? If we pulled that 2 down here and took the derivative, isn't that a 6x? Okay? And this is the whole idea behind what we call the chain rule. Okay? Is that we actually have to take two different derivatives in the same problem. Okay? The first step of the chain rule is to look at the outer function, the squaring function. We're going to bring the 2 out in front, rewrite all of this to the first power. That's the outer derivative. And then all we need to do on the chain rule is we multiply by the derivative on the inside function, which in this case happened to just be 6x. And that's the answer, and this works every time. Okay, that's the chain rule. Now, what if we were going to do this example over here, the square root of 9 minus 4x? Okay, so what if we're going to take, and I'm just going to relabel this as h of x. Okay, so what if we want h prime of x here? Okay, well, first of all, what is my outer function here? Square root of x. And how do we think about square root of x when we want to take a derivative? To the what? To the 1/2. Right. We usually want to think about it as a fraction power. Okay. So what would I do to take the derivative of something to the 1/2? Okay. 1/2 comes out front. And then my something gets raised to what power? To the negative 1/2. Sure. Okay, that's my outer derivative. 1/2 times all the stuff inside the parenthesis to the negative 1/2. Now, does the stuff in parentheses have a derivative? Yes, so we need to multiply by whatever that derivative is, and what is it here? Negative 4. Okay, so the answer for this function's derivative, okay, according to the chain rule, it would look like this. Now, back of your book, we'll probably take one more step and simplify this, and this is probably what it would look like. If you ever have multiplication of numbers, they'll probably put those together. So 1/2 of negative 4 is negative 2. And then if they ever end up with negative powers, they will usually move them to the denominator. And so what we would see on the bottom is the square root of 9 minus 4x. In other words, we move it to the bottom, it makes it positive 1/2 power, and we can rewrite positive 1/2 power as square root. Okay? And so this would be probably the result that you would see in the back of a book. Okay? Okay, so there's a couple of examples of chain rule. Let's continue to look at a few more of them here. Let's see which one I want to do next. Okay, what if we've got this example? S of t equals 12 times 2t to the 4th plus 5 raised to the 3/2 power. Okay. Again, the first thing we have to recognize, is this a composition of functions? Do we have an inner function and an outer function here? And again, the answer is yes. We have an inner function here, and the outer function is raise it to the 3/2. Okay? All right, so what is our derivative, s prime of t here? Well, we start with the outer function. I recognize I have something to the 3/2. So how do we take the derivative of something to the 3/2? What do I do with the 3/2? Comes out front, sure. Okay, so I need to take 12 times 3/2, which would be 18. Okay, so I have 3/2 coming out front, 2t to the 4th plus 5 to the what power? 1/2. I want to take away a full unit off of this power, and so it drops down to 1/2. Okay, I'm not finished yet, but that's half of it. That's the derivative of the outer part. Now I ignore the outer part, so I ignore the 3/2, and I just multiply by the derivative of the inner function. And that derivative would be what? 8t cubed. Sure. Okay. And again, this is my answer. This is correct. Again, the back of the book will probably go through, and they'll probably multiply this 18 times this 8t cubed. Okay? And so whatever that comes out to be, I don't know what that is, but multiply these together, they'll probably put that together and then rewrite this as a square root over here. Okay? That's the result. That's what chain rule is. Now, it doesn't seem too bad. Chain rule's not so bad, but the most common mistake that I see students make is to do something like this. Okay? And you probably don't want to write this in your notes, okay, because then you might accidentally look at it and think that's what you're supposed to do. Okay? The most common mistake that I see students make on the chain rule is to do this. They recognize to bring the 3/2 down and multiply, which is 18, okay? And they recognize that this should be to the 1/2 power, which is good, okay? But what they will do is, instead of rewriting the inner function as it is, they'll combine the two steps together, and they'll take the derivative of the inner function and put it on the inside here, okay? So you've got all the components there, but you're not doing them in the proper order, okay? Just remember, we have to do this one step at a time. That's why they call it the chain rule. You've got one link at a time as you're working through this here. Okay? So we've got to take the 18, we leave that function as it is to the 1/2, and then we multiply by the derivative. Okay? So just remember, one step at a time, and then you'll get the correct answer. Question? Why to the 1/2? Okay, good question, right? This is, right now, the original function is to the 3/2, or which would be equal to 1.5. Whenever we take a derivative, no matter what the number is, we always decrease the power by a full unit. And if we take a full unit away from this, that drops it to 1/2. Okay? All right, another example here. What if we look at this one? Y equals x cubed plus 2 times x squared minus 1 quantity squared. All right, this one gets a little trickier right away here, because first thing I recognize, what's one of the rules I will have to use here? A product rule, right. I have one function times another function. But within the product rule, what will happen over here when I try to take the derivative of this second piece? Then I'll have to do the chain rule, won't I? Okay, because I have a composition of functions over here. All right? So this one will be a little confusing because we've got the product rule is our major rule, but within there we'll end up doing a chain rule. So just got to be really careful with this. All right, let's see how it works. Okay, our product rule says to take one of the components, so I'll just rewrite the first one, and multiply by the derivative of the second one. Okay, so I'll ignore this. What's the derivative of this second piece here? 2 comes out front. X squared minus 1 is to the first, and then I multiply by what? By 2x, because this was my chain rule, right? Okay, so I've got my first component times the derivative of the second, and like I said, that's where the chain rule came in. Okay, then plus, I write the second component as it was times the derivative of the first, which is what? 3x squared. Okay, this is my derivative. Now it's not simplified very much, but this is the actual derivative. Okay, and like I said, this gets a little confusing when you start to have to do two rules at once. I told you the other day, if you can try to avoid like a product and a quotient rule at the same time, you try to do some algebra first so you don't have to do them both. On the chain rule though, it's almost easier to not multiply this out and do the algebra first, because then you'd have three things times each other, because we'd have this times x squared minus 1 times another x squared minus 1, which is confusing enough in and of itself anyway. Okay? So this is probably the most efficient and best way to take this derivative. Now, I do want to look at factoring and simplifying on expressions like this, because again, our goal here in a little while will be set this equal to 0, and we need to be able to clean this up so we can get the easiest way to get those answers. Okay? Well, what factors out of these two terms here? Okay, I can definitely take out an x squared minus 1. Okay, I could remove that x squared minus 1, and I still have one more of them left over here. Okay, anything else that factors out? I see one more thing. What else does this term still have and this term still have? They both have an x in them, don't they? This one has an x right here, and this one has an x squared, of which I can take one of them away. Okay, so I just removed one of the x's. Okay, now what is left from the first term that I did not factor out? First of all, how much of a number do I have left? Okay, I got a 2 from here, and I've got a 2 from here. It's all multiplied together, so that's a 4. Okay, and then I still have this left here, don't I? Okay, so I'm going to take 4 times each one of those. I'm going to kind of do a distributive property here. So I got 4x cubed plus 8 left over on the first one. Okay, what do I have left over here from the second one? Okay, well, what about in terms of a number, first of all? Just a 3. I have x times x squared minus 1, or we could actually have done the 3x times that. So what will I get when I distribute that? 3x cubed minus what? 3x, right. And you may need to write down more steps than I did here. Okay? But that's okay. The ultimate goal, though, is that once we have all of this written out, we want to try to put all of our like terms together, because then we might be able to factor some more stuff out. Okay? Because here's x squared minus 1, here's an x. What do I get when I put this stuff together? Well, I get a 7x cubed minus 3x plus 8. Okay? Now this particular example, this did not factor anymore. Okay? But occasionally when you start putting things together, I got a plus 8 here, maybe on the other side I'll get a negative 8. Those will cancel off, and I might be able to factor out another x or something. Okay? But for right now, this is all the further we could go with this example. All right, good. So there's example number, okay, let's see. Okay, what if we do this one? Y equals negative 5 divided by 2x cubed plus 1 quantity squared. All right, again, what is my major rule that I need to use here? Okay, quotient rule, right? I've got a numerator and denominator, but then within the quotient rule, I will have to do a chain rule, won't I, on that denominator? Okay, all right, so let's work this out. Okay, what do I start with on my quotient rule? What's the order on this one? The order is very important here, so. Do I start with the numerator or the derivative of the numerator? Okay, I start with the numerator as it is times the derivative of the denominator. Wait, let's see, did I do that right? No, I did it backwards, didn't I? Yeah. Okay. We want to start with the derivative of the numerator, right? So the derivative of the numerator is 0 times the bottom component. Bottom times derivative of the top, yeah. Okay. Minus the top component, okay, so minus -5 times the derivative of the bottom. All right, now here's our chain rule. What's the derivative of the bottom? 2 times 2x cubed plus 1 to the first, and then times 6x squared. Correct. The derivative of the inner function is 6x squared. All divided by, what will this be when I square it? If you square something that's already squared, it is now to the fourth, right? Okay. Now, on this example, I see right away this whole piece just zeroes out because I have multiplication by 0. And so up in the numerator here, I'll try to put this together. Let's see here. Negative and negative is positive. 5 times 2 is 10, times 6 is 60, x squared. And I'm purposely not going to FOIL this one out. And does anyone see why I would not want to FOIL this out? Yeah, because I can cancel it off with one. I got 4 copies of it on the bottom. I can actually cancel one of those 4 off with this one here. And so the best answer that we can probably come up with here is 60x squared divided by this factor raised to the third. Okay? That's probably what the back of the book would look like. Okay? Now, I also want to mention one more strategy on an example like this. Quotient rule worked fine, and there's nothing wrong with using it, but what if I was to rewrite this function? And the only reason I'm saying I can do this is because notice the top does not have any x's in it, does it? Okay? If I was to rewrite this function as -5, 2x cubed plus 1, how could I rewrite that to the what power? Negative second. Okay? And now do I have to do a quotient rule anymore? No. Do I have to do a product rule? No. Okay? I don't have to do any special rules if I rewrite it in this form because now all I've got is a number times a function. Okay? So let's go ahead and calculate the derivative this way. We'll compare it to this answer, and I'll show you how much faster it is if we notice the simplifying first. Okay? So I'll just pull this straight down here so it's right next to this answer. Okay? What would be the derivative of this? Well, -2 comes down front. -2 times -5, 10, times 2x cubed plus 1 raised to the what? -3. And then what's the derivative of my inner function? 6x squared. Okay, is that answer equivalent to this answer? Okay, if we look at it real quick, we got 10 times 6x squared. Well, there's our 60x squared. Here it's just written in the denominator. Here it's written in the numerator. And look how much faster it was to get to this result than having to go through a big quotient rule. So if you see little tricks like that, where you might be able to take something in the denominator and rewrite it as a negative power in the numerator, that can actually be a good thing. That can save you a lot of work, save you from having to go through so many rules. Okay. All right, any questions? Okay, we'll stop here for today. We'll probably do some more examples of this next time.